All right, we have the last work in the time succinct randomized encoding morning, and then we'll hear from Giulio about latest, fresh out of the oven result on this slide.
Thank you. Thanks for inviting me. I'll talk about succinct randomized encodings from lattices. This is a talk that is based on joint works with Damiano and Lenz, who are also here. But I should mention that you will not find exactly what I'm saying on any of our papers. I try to present it in a slightly different way. Okay, so I'll start by defining what randomized encodings are. I'll be quick since you've seen already this definition, but if some has missed the previous talk, just let me define this. So I'll consider Boolean functions, so one bit output function, and a randomized encoding consists of two algorithms: an encoding algorithm that takes as input f and x and outputs an encoding of f and x, and a decoding algorithm that recovers a message out of the encoding. Now, we want three properties from randomized encodings. Correctness says that the decoding algorithm should return correctly the evaluation of the function f on input x. Security says that the encoding itself should be simulatable only given the output of f of x and f. So just as a note, this in particular means that I will consider a setting where the functions is public, and the only thing that we are concerned with is protecting the security of the input. You can, if you care about the security of the function, you can do that via standard transformations, but let me not go in that for this talk. But yeah, so far the notion is of course trivial because you could just set the encoding to be f of x. So I need to require something more from the encoding scheme. And the third constraint is what I'm calling here complexity. And so there should be a sense in which the complexity of the encoding algorithm should be less than the time to evaluate f. Otherwise, the scheme is trivial. The sort of more classical way to think about this would be, for instance, for the encoding to be to have less depth of the evaluating f. But succinct randomized encodings have a stronger requirement. But before I say that, let me also say that for succinct randomized encoding, you have to be a little bit careful about the kind of computational model you're considering. It doesn't necessarily make sense, this notion, if you are thinking of a function as a circuit, but you actually have to think of a function as either a Turing machine or a run program, so in the sense that the description of the function itself should not be as long as the time it takes to compute it, okay? So I'll think about my function as being computed by a program P in t steps and using M memory. So I'll consider run programs in this talk. And in this context, we want that the complexity of the encoding algorithm should be sublinear in T and also ideally sublinear in M. But let me also mention that other notion of succinct randomized encodings where you don't constrain the complexity of the encode, but just the size of the encoding are also meaningful. Okay. Succinct randomized encoding are very useful. There are many applications. Let me not spend too much time on this, but just to mention, secure computation. Succinct randomized encoding is essentially a succinct version of garbled circuit, so it's a very useful tool. Delegation, right? So succinct randomized encoding can be thought of as a one-round delegation. Right? I want to compute the output of a function and give it to you, but I don't want to do the work. I just give you a succinct randomized encoding for it. Time lock puzzle, we've seen this at length. And then let me also mention that succinct randomized encoding allows you to turn an obfuscation for circuit into an obfuscation for Turing machine or run program, depending on the randomized encoding. So it's a fairly easy transformation. So these are the applications. By the way, I should mention that my talk is timed for about 45 minutes, so there should be plenty of time for questions. So feel free to interrupt me at any point in time if you have questions or concerns. Okay, so let me say a little bit about what's known, just a brief recap. So there is, to construct succinct randomized encoding, we have the so-called obfuscation approach, which, well, I called it this way, which is sort of the maybe historically first approach. You know, a series of work has established that using obfuscation, we can construct succinct randomized encoding with essentially optimal parameters in terms of, oh, sorry, this should be a T, in terms of runtime and memory complexity, okay? And again, I'm thinking about Boolean functions, so that I didn't put explicitly the output dependency in this slide, but it should be there, of course. Okay, so these works actually construct a stronger primitive. Typically, they construct indistinguishability obfuscation for RAM programs or Turing machines. So which is the difference is roughly that in indistinguishability obfuscation, you can evaluate any input of your choice, whereas in succinct randomized encoding, you are fixing an input. So there is hope to do actually better in terms of you know, assumption, and so that's why we had this hope, and there is the so-called, what I'm calling now the lattice approach, which the ambition of this approach is to obtain quote-unquote direct constructions of succinct randomized encoding from more or less established lattice assumptions. And one upshot, of course, of this approach is that you could give a candidate that withstand quantum attacks, depending on how you feel about the quantum security of lattice problem. Yeah, so we have seen this already, but let me say it again. So there are two works that follow this approach. Our work at Crypto last year that gets a square root complexity, sorry, a square root dependence in the time, and you know, linear dependence in the memory. And the previous talk that we saw that improves the square root to any constant. Okay. So what I'll talk about today is another approach that follows this line of work that reduces the complexity of the randomized encoding to be polylogarithmic both in T and M. Okay, and so the formal theorem statement that I'll try to prove to you today is that if a circular variant of the decomposed LWE problem is hard, then you have succinct randomized encoding with close to optimal complexity. You could do slightly better by putting a plus here, but maybe if you don't care about that, then it's roughly optimal. And maybe let me not be too precise about what this assumption is. I'll maybe defer the discussion towards the end of the talk. Okay. Good. So that's what I want to show. And actually, I will make my own life a little bit easier, and I will not show you a construction of succinct randomized encoding, but I will show you a construction of a primitive that I call witness encryption for P, with the same complexity. So what is witness encryption for P? It's what you think it is. So it allows you to encrypt a message M with respect to a program P and an input X. And here, I'm actually thinking of my program, both my program P and my input X as being completely public. And so the only secret that I want to protect is the message M. Yeah? So and I want two things. So first thing that I want is that if the program evaluates to 0 on that given input X, then I can actually decrypt the message. So here I sort of flipped maybe the acceptance and rejection. So acceptance for me is 0. It's sort of more natural in the lattice setting, but you can ignore that. And the second point, of course, I want is that if the program outputs 1 on input X, then I want my message to be computationally hidden. Yeah? And again, let me stress that this notion is meaningful only if I impose some constraint on the complexity of the encryption algorithm. Because otherwise, you know, I can just evaluate my program on input X, check whether it accepts or not. Now, if it accepts, I just output the message. If it doesn't accept, I just output bot. Right? So it wouldn't be an interesting notion. But if the encryption algorithm does not even have time to evaluate the program, then it's a meaningful notion. Yeah. So that's what I'm going to build. Yeah, fortunately for us, it turns out that this notion is essentially equivalent to the notion of succinct randomized encoding. So once you build this, there's not a lot of work to do in order to get the succinct randomized encoding.
That sounds almost identical syntactically.
Come again?
What's the difference?
Between the two?
Between the two, but it sounds almost...
Yeah, so,
Right, yeah.
so in succinct randomized encoding, you want to protect the entire input X. Here, X, I'm thinking it of as a public.
CMP versus FE.
Yeah, so think, if you want, you can think of it as an attribute-based version of succinct randomized encoding.
And by the way, is it easy to see that IO implies succinct randomized encoding?
No, I mean, it's not, right? I mean, I think, these works are, this long series of work that I mentioned, they essentially construct a succinct randomized encoding from IO. Once you have that, going from IO for Turing machine is sort of an easy step. Maybe one easy way to see that, at least heuristically, he would imply it, you can think of obfuscating the function that sort of synthesizes the garbled circuit. And then, then you make the randomized encoding succinct, just by not giving it explicitly, but just giving a circuit that sort of synthesizes. I hope I said it correctly. Makes sense. Yeah. Good. But again, proving it is what makes the problem difficult, I think. Okay. So witness encryption for P. If I construct this, I can construct succinct randomized encoding. Again, these two primitives are essentially equivalent. This direction is it's obvious. You can do it as an exercise if you want to practice, but it's easy. This one is less obvious, but it follows from standard, I would say by now, standard cryptographic techniques. And here the idea is, to protect now instead, since your computation is correct, you want to protect the since your computation is now public, you want to protect the privacy of your computation by just doing it homomorphically. Then you have to work a little bit harder to give away the output, but that's sort of the intuition. Okay.
You stated the implication, but so what is the result? The result is witness encryption for P implies succinct randomized encoding for M?
Yeah.
Or without any assumptions?
Sorry, with LW. With LW.
Even for this implication, you still need
Yeah, you need fully homomorphic encryption.
Oh, FHE. So FHE plus witness encryption for P implies succinct.
Right. You also need garbled circuits, which is implied by FHE.
Is witness encryption for P also known as message hiding encoding?
As what?
As message hiding encoding?
I'm not sure. Maybe. I wouldn't be surprised if someone already, formalized this notion. I'm not aware of this, but maybe I just missed that word. Yeah. Let me say that there is maybe nothing very theoretically deep about the definition of witness encryption for P. It was just a way for us to, just a convenient interface to work with. Yeah. Okay. So let me give you an outline for the rest of the talk. As a first step, I'll recall some properties of the homomorphic encodings, just as a recap, and we will construct a witness encryption for P, which doesn't quite satisfy the properties that we want, but just to practice with the formalism. And then we will upgrade these encodings to the so-called rate 1 lattice encoding, which I'll show you what they are. And finally, I'll show you how to evaluate homomorphically RAM programs over this lattice encoding as opposed to circuits. And this allows us to connect to a bootstrapping theorem, which is very similar to what we've seen in the previous talk. I'll give you, I will not spend too much time on this since we've seen it already, but maybe I'll give you one slide for an intuition. Okay.
Again, if you replace RAM by TM, this is also a new result, right?
Yeah.
What to TM? So why jump through two hoops together? Why not just?
Yeah, we just could do it for RAM. It was not much more difficult than do it for TM. So. Yeah. I don't think the construction simplifies dramatically if you consider TMs, I think. Yeah. Okay. sorry, more questions before I proceed? Okay, so now I will show you a construction of witness encryption for P, which does not exactly satisfy my properties, but again, to practice. So the only ingredient that I need is the following equation. Again, this is sometimes called the key equation for lattice encodings, for homomorphic lattice encodings. And it says that for all matrix A and input X and all circuit C, we have two low norm matrix, H and K, that satisfy this equation. The emphasis is on the fact that the matrix H depends on the circuit description and on X, whereas the matrix K only depends on the description of the circuit. This is the bread and butter of a lattice homomorphic encoding. Okay, so I'll leave it here just for us to stare at it for a second. But once you have this, it's pretty easy to construct a so-called, I should mention that this matrix G here is just the gadget matrix, which is the inverse of the binary decomposition operator. I think you probably have all seen this, but just for those of you who have never seen this notation. So once we have this equation, it's actually pretty natural to construct a witness encryption for P that doesn't work, but let me say how I do it. So I will multiply from the left this side of the equation by a randomly sampled vector S, which I'll think about it as my secret. And again, X is my predicate. And I will add some random Gaussian noise. So this is the first term of my ciphertext. Whereas the second term of my ciphertext will be taking essentially this term of the equation multiplied from the left by the same vector S. And I'll also sandwich it from the right by a binary decomposition of a random vector U, which I'll think of this random vector U as just a public random vector. There's, you can think of it as fixed in the sky. There's nothing secret about this U. Add some independently sampled noise and some encoding of the message. Okay, so this is my ciphertext. Okay, I guess I should mention here that this is essentially an attribute-based laconic function evaluation encryption, for those of you who are familiar with it. But I want to call it a witness encryption for P. So that's, again, my encryption of M with respect to C and X. Good, so I have to show you two things. I have to show you that if C equals to 0, I can recover the message, and if C equals to 1, then my message is hidden. Yeah, so let's go. Let's proceed. So if C equals to 0, what can I say? Well, I can use this equation here and multiply this term by my low norm matrix that depends on C and X, which I know. They are both public. And I can ignore this noise term because, again, H is low norm. So the product of these two elements gives me something close to S times A K sub C, applying this equation. Yeah? Now, once I have this term, I can multiply it from the right by this public binary decomposed vector and subtract it from this term. So this subtracts the mask. What is left is an encoding of the message plus some noise, which I can, from which I can recover the message using standard decoding techniques. Yeah, so that's easy. Those correctness. I actually want to show you the more or less full proof of security for this. So in this case, C of X is 1. So what can we say? Well, we can apply again the equation. So now it's a little bit more complicated, but maybe you can trust me that this term here, by applying this equation here, equals to this. In particular, note that here there is because C of X equals 1, there is an extra term, which is S times G inverse of U. Well, G times G inverse is the identity, so this is nothing but S times U. Yeah? Okay. So now the next thing that I will do, I will change this matrix, A plus X tensor G, to be, I will just rename this matrix to be A tilde. Yeah? And I expanded here my relation. So that's just a syntactical change. Great. And now, okay, now I'm almost done because this is already an LWE sample, so it looks a little bit promising. So what I will do, I will sort of add an extra term an extra noise term here, which I can do by some standard statistical argument, and so express this term as something close to an LWE sample, then something that I can publicly compute from this LWE sample, plus another LWE sample. Okay, so now this is uniform by LWE. Yeah, this is something I can compute publicly from this sample. And this is, again, uniform by LWE with the same secret. And okay, crucially, U and A are independent. Yeah, so now I can conclude that both are uniformly sampled. Excellent. Okay, that's the proof strategy. Okay, great. So of course, this is not exactly a good witness encryption for P, even for circuits. And I'll tell you why. So there are many problems with it. Let me list them in no particular order. So the first problem is the noise growth. Maybe this is somewhat minor, but let me put it here. So the point is that all of these equation that I liberally ignore the noise. I mean, you can do it up to a certain point, right? So the noise keeps growing as the norm of the H matrix grows. So this imposes, at the very least, a strict bound on the depth of the circuits that I can evaluate on this witness encryption for P. So this is not something that I want for reasons that will become clear later. But this is actually solved by the talk that we have seen this morning. They essentially have a bootstrapping technique that allows you to sort of refresh the magnitude of the noise, and that removes the bound on the depth. Okay, I will not go into this technique, but let's just keep in mind that this is possible. Okay, one thing that I wanna mention here is that this introduces an additional circularity assumption for the same reason as articulated in this work. And that's actually where the circularity part of the assumption comes in my previous slide. Okay. Again, I don't want to be too precise about this part because it's really not the focus of our work, so I'll sort of ignore it for now, but just keep in mind that this thing exists. The other problem is that this only works for circuits, whereas I advertise something for run programs, so I should fix that. But the biggest problem of all, which is the reason why this is not a good witness encryption for P, is that computing K sub C just takes as long as evaluating C. Okay, so this is by no means a good witness encryption for P, because in order to compute this term, I need to do as much work as evaluating the circuit itself. So forget about run program. This is not even a good witness encryption for P for circuit. Okay. But I claim that it's still a useful starting point. This particular problem will be solved with the bootstrapping technique that we shall see later. Except that now this bootstrapping introduces a new problem in the sense that in order to make the parameters work, we actually need our encoding to have a good rate, where the rate is defined as the size of the ciphertext compared to the size of the input x, right? So this is not a good rate because for every bit of x, I have, let's say, polynomially in lambda bits on this ciphertext. So it's actually very important to have a rate that approaches 1 in order for our bootstrapping to work. Yeah? So again, this is a problem that will show up later, but I will solve it. So now I will solve it by showing you a procedure that allows us to evaluate run programs and simultaneously improves the rate of the lattice encodings. Okay? And again, you can ignore this lower component and just focus on the first component. Okay? The lower component is just the mass that you will subtract out at the end anyway, so it doesn't really matter for evaluation purposes. Yeah? So that's sort of the important part of the talk. So if you've been asleep, it's a good time to wake up. Okay, let's go. So let me say one thing before starting. what is a run program? Well, a run program consists of a step circuit, right, that does read on a database, yeah, and then writes on other location, potentially other location of the database. That's a run program. So I want to think of X now not as my input, but as the entire memory of my run program. Yeah, this is without loss of generality, of course, because I can always, initialize some of the bits of my memory to be my input. Yeah, so it's not a significant change, but conceptually maybe it's a little bit different from just evaluating circuits. Yeah, so I will start by instead of encoding X in the clear, I will encode a hash of X. So this is the same encoding as before, except for a hash of X. And the hash is just the following linear function, which is the subset sum of some publicly sampled matrices BI. Yeah, good. So, and additionally, I have to give these matrices in the clear, and plus I will add to my encoding these mysterious Cij terms whose purpose will become clear in a moment. But so just keep in mind for a second that this is my encoding for X. Okay. Now I have to show you two things, and then you should be hopefully convinced that we can evaluate run program. So I want to show you first how to read an address from the memory, and then how to write an address from the memory. So, right, if I show you both of these, then we're sort of done, right? Because the step circuit is a circuit, so we can evaluate it using the techniques that we've seen already. And so the only two things that are non-trivial is to read and write from the memory. So let me start with the write. So let's imagine we want to read, with the read. Let's imagine that we want to read the ith database entry. And of course, the problem is that here we are stuck with the hash of the database, right? So we don't have that in the clear. So what do we do? The first thing that we do is that we actually use the circuit evaluation procedure to compute the product of di times the hash. Yeah? So this is a well-defined circuit. Di is a public variable that I can hardwire in my circuit. And so using the standard good old lattice encoding for circuits, I can actually compute this function. Yeah? So far so good. And the next thing that I do, I will just sum this hi that I just computed with the sum of all xj times cij, which are these terms here, which I gave it as a part of the encoding. Yeah? And actually, you can do the arithmetic. I mean, I did it for you, but you can check that this is indeed correct, that essentially this term cancels out with this, and all you have left is s times ai for some matrix ai, plus xi times g, which is precisely a lattice encoding of the ith element of the database. Yeah? So this allows me, this public procedure allows me to transition from a lattice encoding of the hash of the entire database to a lattice encoding of the content of the database at position I, which is precisely what I want for read. Yeah? Makes sense? So far, so good. Great. What about write? So write is based on a similar observation. So let's imagine that we want to write the ith database with a new entry xi prime, whereas the old entry was xi. So here the observation is actually pretty simple. It is based on the fact that our hash function is essentially just a linear function. So if you imagine the new hash that we want to compute of x prime is nothing but the hash of x plus bi times xi prime minus the contribution of xi, which was the previous value in memory, so that this subtract away from here, and then I get the right hash. Yeah? So this is actually very simple now because we know how to compute. We have an encoding of this. Yeah, this is something that we can compute easily, again, using the circuit homomorphic properties of our lattice encodings. And so computing this and subtracting it away from the encoding of the hash of x, we can obtain a honest-to-God, well-defined encoding of the hash of the new state of the database. Yeah?
The circuit is
evaluates what?
It just computes this component, and then sums it to whatever input is here.
Why? What, the circuit, I mean, this is something that you can do on your own.
Right. So, but the point is that we want to keep the evaluation. So we want to keep the invariant that our state of the computation is encoded in this form.
Okay.
Right? So otherwise, we will have problems at later steps. It is true that this is something you can compute on your own, but you have to make sure that you have the encodings in the right format. And by the way, in the actual evaluation procedure, we'll have to do both, because you have to maintain a consistent state of the database. So outside in your head, you will just operate in the plane on your database, plus keep this consistent, the lattice encoding consistent with your database.
So do you, the RAM can be, you don't need to know I.
No, you need to know I, right? Because you need to know which index.
Okay, so why isn't this revealing? You use an ORAM or?
No. So remember that there is nothing private about the computation. Remember, there is nothing private about the computation. I want to do a witness encryption for P.
Okay.
Everything is fully public, and so I don't need to worry about that. Yeah.
I missed it. The CIJ has this delta IJ. What is a delta IJ?
Oh, that's just Kronecker delta. It's 1 if I equals j and 0 otherwise.
Oh.
There is, but I think you pointed to one issue that I'll get to later.
You've been around physicists too long.
Come again?
You've been around physicists too long.
Is this a physicist thing? I mean, my fault. It was actually my name. By the way, my as a sort of insider thing, my proposed name for the assumption was actually Kronecker LWE, but Damiano and Lenz did not like it, so I had to concede. Anyways, so that's what you missed. Okay. Anyways, let me briefly recap what we've done so far. Maybe this helps getting back the intuition. So again, we are doing a homomorphic evaluation of RAM program as follows. For every step, we read the value from the database. We homomorphically evaluate the step, whatever the step circuit tells us to do. And then the output of the step circuit is an index and a new value that we write in the output of the database. Then we repeat. And the important thing, as we said earlier, is that we maintain the invariant that the encoding of the hash, that we have an encoding of the hash of the current state of the database. Yeah? So that's how we sort of do our homomorphic evaluation. Yeah? Any questions about this? Wonderful. Okay, so now what? Are we done? Well, there is actually a problem, and that goes against what I advertised in the beginning. So in particular, if you look at the public parameters that you need in order to specify these entire hash functions, you actually need one matrix per memory location. Yeah? So in particular, this means that this parameter m is actually the size of your memory. And so this means that this size of the encoding here is way too large to be logarithmic in m, as I told you in the beginning. Okay, so what do we do? Once you have seen this, the solution is probably not very surprising, but it's essentially just doing a recursive version of this construction. So we just do, instead of, so again, the problem is that this hash function is just a linear function in the common reference string, but that's not the way we know how to do hash function. We do Merkle trees. Yeah? So that's exactly what we're going to do. And I claim that actually what I've told you already, it's almost sufficient in order to understand the evaluation of RAM programs even with this recursive construction. So we end up in a situation like this. Let's imagine that we have x1, x2, x3. Then we apply a Merkle hash. Then we hash the hash, and we are at this point. Yeah. So and I don't want to repeat both of the algorithms. So I'll just show you how to do read, starting from a lattice encoding of the hash of the root of the hash. Yeah. So I have this. But I've already showed you a procedure to turn this into a valid encoding of any of the preimages. Yeah? And so in particular, imagine that now I want to get to an encoding of x0. So the first thing I'll do, I'll apply the previous algorithm in order to get an encoding of h0. Yeah? H0 is, in fact, is half of the database that we saw before. And so, using the procedure that I showed you before, we can actually transition from an encoding of the root to an encoding of this hash. Yeah? And then we can keep going, right? So it's, again, using precisely the same algorithm, now we can follow the path towards our x0, and eventually we end up with an encoding of x0. Yeah, so it's nothing too esoteric. Okay, I should mention that I oversimplified a few details. So the actual construction is a little bit more complicated because there you want to handle indices which are also encoded. But okay, this maybe. If you wanna see that, you can look at the paper. I think for getting an intuition, this is perfectly sufficient. Yeah.
Since the memory will store all the hashes will be the new memory will be all the hashes. So now it's like
right.
It's linear block, but that's fine.
Right. So again, we will always think of the actual computation as doing the same computation that we're doing encoded, but in the plane. So I'm imagining the decryptor to just keep this entire state in memory and then locally access what needs to be accessed.
Then for initialization, I'm trying to see.
Oh yeah. Yeah, good point. Yeah. Okay. I didn't want to say. I didn't want to go there, but okay. So good for initialization. So it turns out that. If you initialize everything to 0, you don't actually have to compute this thing explicitly, because if a big portion of the memory is 0, everything is 0 anyways.
So it's linear, like
because the hash is linear. Yeah.
Hash of 0, 0.
It's that's actually it's actually important for
the errors. I mean, you need errors. Oh no, the hash doesn't have errors.
No errors for that. But one thing that you need is that things remain small, right? So the hash is only collision resistance if the input is, has low norm. So you have to be careful about that. But maybe let me not be too precise about this. Yeah. So far so good. That's basically it. Great. So we can summarize what we have achieved as following new quote-unquote key equations. So namely that for all matrices A and for all input X and for all run program P, we again have low norm matrices H and K, precisely the same as before. H depends on the program P and on X, whereas K just depends on the program P. That respect this linear equation. The only thing that is different is that now we have these extra terms, as we saw before. Yeah. Note that before we had I and J run over from 1 to M, but that's because we were doing things in a linear way. For Merkle tree, I and J just run over, let's say, you can make it even a constant size domain. So it's not, there is no really no memory dependency. Yeah. Okay. Yes.
So I think back to what Moni was asking about, like this position. So this position is not leaked in K of P at all. So the K of P is independent of these positions.
No. So
that you're reading.
So I mean the program dictates the positions that you're reading, right? If you want, you can assume without loss of generality that the access pattern of your program is fixed.
It's fixed. Okay.
It doesn't change much. Yeah. Okay, so now we have our new key equation, so we can try to do the same recipe as before. So we have now an encoding of hash of x. This is the same term that we had before, except that now we have kp instead of kc. And now we, of course, need to have these additional terms, which are the now hopefully less mysterious terms that we added to the ciphertext.
What is the I and J? Is it constant?
It's, yeah, you think of it as constant. It used to be m, now it's constant.
You're saying they could be used at all levels semantically.
Yeah, yeah, I think so. Yeah, I think so. They can be reused. Even if they cannot, it would still be fine because it would be just logarithmic. But yeah, but they can. Yes.
Now succinct size.
Yes, but not succinct. Yeah,
Succinct.
I'm getting there.
It was already succinct size in BGG, but now it's succinct in the attribute size.
Okay, so good. So what did we gain? Maybe let's go over this. Yeah, so good. It was already succinct. Now it's super succinct in terms of x, right? So we don't have any more dependency in the length of x. And now, okay, now we can also evaluate run program as a bonus. That's what we have gained by doing all these shenanigans. But you're right. The next problem is that, I mean, this thing still takes long to compute.
The evaluation time is the run complexity.
Yeah, exactly. I mean, but it still takes long, right? And I need to compute this k sub p in order to compute the mask here. So far we haven't really, yeah, we're not done yet. Yeah. Okay, so now what? So the point is that it is true that this takes long to compute, but the main observation is that actually this can be reused. Yeah, so this doesn't depend on the input. Yeah. You know, it can be reused across several run programs. In fact, if you think of a universal run program, you can always, you know, think of it as just the same description of the program repeated itself. What changes is the state of the computation, but the program is always the same.
Before you go on, just
Yeah.
want to clarify this step. Do you need new assumption, or this is circular WE?
For what?
For this step, up to this step, do you need any new assumption, or this is already?
Yeah. So if you let's say didn't wanna do the bootstrapping, here you already need all the assumptions that I said. Yeah. I mean, unless you're okay with the depth dependency, then you don't need the circularity, but you still need decomposable LWE. So decomposable LWE is roughly because of these terms.
I see.
Just a quick question about the RAM versus Turing machines.
Yeah.
In the context of when you have non-determinism, then RAM, you know, can be simulated by Turing machines. So can't you use this to sort of generically bootstrap the Turing machine to RAM?
So I think
by checking the advice.
But so yeah, I'm not sure non-determinism is allowed here.
For the evaluator.
Yeah. So you need to fix the program and the input ahead of time. I think that would be the problem. Did I say that correctly?
Yeah.
Thank you.
The reason why you want RAM is for what is gonna explain now. Like if you have the dependency on the size of the memory, like the total computation blows up because we will use recursion.
Yeah. Okay. More questions? Good. Okay, so again, the intuition is that yes, this takes long, but it can be reused. So ideally, we want to compute one of them and then reuse it across several such encodings. How do we do it? Again, I'll just do it as a cartoon because that's essentially the same ideas as you saw in Rachid's talk, so I won't go too much in the details of this. But roughly speaking, what we're doing, we're thinking of our computation as a line. You start from x and you end up at pt of x. This notation means t steps of the program p. Yeah? And I will consider the midpoint of the computation. We'll slice the computation in two and look at this the state of the computation after step t divided by 2. Yeah? Now, if we start from an encoding of the hash of the database x, okay, then we know we can compute compute any program homomorphically. So in particular, this will allow us to compute p of t divided by 2. And let's say, roughly speaking, doing half of the computation. And now we'll set things up in such a way that at this point, we will not just obtain a bit, but we will obtain a new encoding for the next half of the computation. And here, it's important that the encoding is a hash of the updated state of the program. So the way you set this up, it's maybe a little bit more complicated than this cartoon picture. Requires like garble circuits and so on. That's essentially what Rachid already said. Yeah. So maybe I'll just leave it at this. Okay. And once we have this new encoding, we can continue the computation all the way until the end. And now the trivial observation is that the program. T steps of the program is just the composition of t divided by 2 steps twice, a trivial observation. And so it suffices to compute this matrix K sub P, not for T, but for T over 2. Yeah? And now we have halved the time to compute it, and now we can just recurse all the way until it's constant, essentially. Yeah? Again, for this, it's very important that the size of this encoding actually does not depend on the size of x. Otherwise, you would have an explosion in the recursion. Yeah? I mean, you still have x in the plane, of course, right? So technically, it does depend on x. But if you remove the x part, which you actually don't have to compute in a quote-unquote secure way, then the size of this is actually independent of x, which is very important for the recursion to go through. Yes.
So I think from the thing that we have in here, like you couldn't do it more than constant number of times, like because of like. Yeah. So here you are doing logarithmic, so it's because of like some space compression, or. I
believe it's actually because of this, because you have an encoding whose size does not depend on x. Yeah.
You probably still. Like, is T over 2 really good enough? Because like there's.
No, it's not. Of course. Yeah, it's not. Yeah, you're right.
To do like T over security parameters.
Correct. T over 2 is not a good idea. So what you actually want to do is you want to slice into enough blocks so that the overall time is half, and then you recurse. Yeah.
To do this, to get this encoding in the middle, do you still need to garble circuit?
Yeah. Yeah, because if you recall, all I'm doing is just a witness encryption for P. That doesn't, it doesn't have any, secrecy except for the message. Yeah, and I need a way for the evaluator to recover magically this encoding, but it better be the case that this randomness S tilde is hidden, right? Otherwise, there is no security. And for that, I need a garble circuit.
This recursion tree, don't you need, in some sense, a garble circuit for every node of the tree? And then would that
no, so
too many garble circuits?
Roughly speaking, what ends up happening is that okay, again, maybe I should say that maybe we slice the computation into lambda slices. So you have one garble circuit per slice, and then times the number of recursive call, which is logarithmic. That's what roughly ends up happening.
So where are you using the fact that the computation of the first half and the computation in the second half are performed by the same machine?
Yeah, so this essentially, let me go back. This essentially allows me to compute not Kp, but Kp of T over 2, which is T over 2.
Okay.
So this technically was Kp of T, sub T. Right? So it's not T over 2, again, but yeah. That's where it comes from.
Okay. So the fact that you're using all the noise terms, usually it's kind of bad, it's not a problem?
No, yeah, it doesn't seem to be a problem. It's actually okay, maybe it's a sort of a philosophical point, but it's somewhat strange because in sort of obfuscation construction, you have to work really, usually the intuition for correctness is simple, but then you really have to work hard for security. Here is maybe sort of the other way around. Like security is somewhat easy. It's not much more difficult than the thing that I showed you before, but then you have to work quite hard for correctness. So I don't know if that answers your question. But
You're not reusing the noise terms because the garbled circuit creates a fresh S and E, right?
Yeah, exactly.
So, but I am reusing this. Yeah, I don't know if you would count that as reusing, but.
So you reuse the matrices, but like then the rest gets re-randomized by the garbled circuit.
Okay, this is a more accurate statement of all. Thank you. Okay, so let me. It's stuck. Oh. Let me jump ahead. Okay, so let me get to the assumption. So the decomposed LWE assumption states, this is the formal version of the assumption, is that these two distributions are computationally indistinguishable. And again, this is the sort of crucial term that you should keep in mind. And one thing that we can say, it's actually not that hard to prove, that this is implied by the succinct LWE assumption. And again, let me stress that if I didn't have this delta, or if these deltas were always 0, then it would be not very hard to prove that this follows from LWE. Yeah, so there seems to be something crucial about this term. We don't know how to prove it from LWE. And here maybe a potentially controversial statement is that this assumption maybe follows a general circular security of LWE. I'm not sure how much I believe this, but okay, let me just say it and put it out there as a sort of general heuristic for reasoning about circular security. Here's one assumption that you could make. It's that you take any m sample from a distribution such that m and Sm plus e are computationally close to uniform. Right? If m is uniform, then this is just LWE. Yeah? But it doesn't have to be, right? As long as you can prove it maybe from LWE, it doesn't have to be uniform. And then circular security says that for any fixed function f is not allowed to depend on m, so it's a fixed function. Then we have that these two distributions are computationally indistinguishable. Yeah? So if you are happy with this quote-unquote heuristic, then this assumption is implied by this. Again, it follows by the fact that if you remove these terms, then we can prove it from LWE. And so for us, the matrix M here would be just essentially the outer product of the A's and B's. Yeah? And you can prove that it's as hard as LWE. Then of course you have to make this assumption. Yes.
What's the degree of the function? Because in circular you normally quadratic and like so what's the degree of the f here in this reduction?
In S?
Linear.
F.
Yeah, it's a linear function, right? It's just this. I mean, just ignore everything else. It's just S times this.
What is the degree in S? Because for linear functions, you can prove it is equivalent to LWE. So
yeah, but
that's what
I think that's only true for random matrices.
Oh, okay.
So I think that's the gap. I think, yeah. So that our matrix M is not random. It's definitely not random. I mean, it has structure. It's a I don't know how to say it, but it's like a low block norm. I don't know. Yeah. Low norm. Okay. Sorry, low block rank. Does that make sense? Okay. So again, I don't know if I believe this, but just to put it there. Good. So let me conclude. I think I'm actually on time. So there's actually quite a lot of application of these techniques that I didn't get a chance to show you, but you can use more or less the same ideas to construct things like Laconic function evaluation. In some cases, you can actually improve the assumptions. You can remove the circularity, for example. You can construct attribute-based encryption for RAM. This requires some extra step because you need to add cryptors. Again, I don't want to talk about it, but just mention that it is possible. There is also a way to get register ABE. If you know what it is, good. If you don't know, it's fine. And the question is whether there are more. It feels like a very powerful abstraction. We try to get what we could out of it, but maybe someone more clever can do better. Open problems. of course, the elephant in the room is try to get things from a better assumption. I mean, ideally, no circularity. That seems ambitious, but okay, we can try. I think that again, the circularity really comes from the bootstrapping step in the homomorphic evaluation. So I feel like if you want to remove circularity altogether, you have to start from there. That's again, it's actually very important for our bootstrapping. I may say bootstrapping twice, but like for our bootstrapping for witness encryption, it's actually very important to remove the depth dependency. So
the I/O route gives us from alternative assumptions with no circularity the same conclusions. So all these conclusions follow from I/O, right?
All of these conclusions follow from I/O. Yes, absolutely. Come again? I think okay. So I mean, removing circularity would be fantastic. Maybe a slightly less ambitious goal would just be to remove decomposed LWE. That I mean, I think that would count as progress. Just to do it from circular security of GSW. Although again, then you are comparing flavors of circular security assumption, so it's maybe not super clear what you gain, but I think it counts as progress. I think something you could do, we didn't do it, but it's probably not that hard to actually do parallel run, if you wanted to. I don't think there's any particular roadblock. I think this should just work, but it needs to be done. A question that I'm very interested in is actually computational model beyond RAM. I mean, I'll leave this to your imagination. What this could be.
Like what?
Quantum. Let me not say anything more. That's it. Yeah. So if you have more, yeah. Thanks for your time.
How do you recurse it?
Yeah, so there are two ways. The way we do it in the paper is just to set the matrices to be low norm as well, so that you just, recurse over the integers. So then it's just a linear function.
So is like the sys hard for integers?
It is.
Is it based on LWE? I didn't know that.
Composite LWE.
Based on decomposed LWE, sys is hard over integers?
Yeah, I think I forget if you have to assume LWE, but I think you can prove this.
Like the composite WE implies LWE.
No, but I think what she's asking is, I mean, you have low norm matrices. Even just the linear function that I showed, is that collision resistant?
Yeah.
Sys over the
follows from LWE.
It follows from LWE.
Yes.
Yeah.
Sys over the integers should be as hard as sys over, because like a solution over the integers is also a solution modulus.
I see.
No, but he was asking for low norm, right? The matrix itself is not mod cube of the integers.
You can prove it with the G inverse, some G inverse shenanigans. You can prove it. I cannot do it online. Let me not embarrass myself. But another way, by the way, would be to do instead of having low norm matrices. I think you could also do it with alternating G inverse with A. I think it would work as well. Then you have to maybe modify a little bit the algorithms that I showed, but
yeah, because like it's no longer linear.
Yeah, but I think it should still work.
It should work.
Could you explain again how to convert the encoding of the hash x into the encoding of x in the, I think, read process?
The read of the RAM?
In the read process of RAM. So how to convert the encoding of hash x into the...
This slide?
I think so.
Okay, so let's start from an encoding of hash, so this is literally this.
Yeah.
And then you want to convert it into an encoding of xi, for some i that you know.
Yeah.
So this is something you can compute starting from this.
Yeah.
Because it's just a multiplication of this times this. So you can think of it as a circuit and then use the other homomorphic evaluation. And then you just subtract hi to this term here, which again you can compute given all the x's and all the c's.
So the point is that if the encoding of this hi is provided, and also encoding of the Cij is provided, or so like evaluator can compute compute this output hi minus sigma of the xj Cij by linear combination if the xj is known, right?
Yeah, everything is public.
Okay, yeah, thank you.
Does that make sense?
Yes.
Just check every step takes the whole memory. You need to. Yeah.
So good. So this is because we did this silly hash function, but exactly. Otherwise, you would have to follow the path.
Is it fair to imagine that basically this technique underneath all of it, it's letting you sort of take BGG plus encodings of hashed values and open it to kind of like any of its Merkle tree openings, in a sense? That's it. Once
I think
tree openings, you can do all the computation on your own.
I think it's fair. Yeah, I think that's pretty much the way we're thinking about it.
It's just a way to expand it.
Yeah, exactly. So you can think of it, I mean, we didn't formalize it, but I think you can think of it as just maybe a compressed version of BGG encodings that allows you to expand it maybe in the directions that you want.
That's what functionally you're getting in both.
Yeah. Again, you have to be careful for, I think, what Evgeny said, because if you do it this way, you pay with a memory.
I understand that part, but yeah.
Yeah.
And one other thing is that technically, I think you probably made this observation in your previous work that if you are working in the pre-processed model for the witness encryption for P, then the previous construction was already optimal because you can compute AC once and then you'll be done with it.
Right.
No matter how many X's you want to encrypt it for.
That's correct. Yeah, that's absolutely correct. So if you are in the pre-processing model,
same works here too. You don't have to bootstrap.
Well, I mean. So I guess in the pre-processing model, then you would have it already for circuits.
Even for your RAMs, you just pre-process. I mean, don't do the bootstrapping too.
But I think for RAM you have to work a little bit harder. But there's a paper from Daniel that does it in the pre-processing model, I believe.
My pre-processing definition is that the pre-processing time will grow with the maximum T. That's my definition.
So we got even worse. It grows with like the circuit. So I think you still need this to get even in the pre-processing model. If you want the pre-processing to just be T, rather than like T squared, rather than pay.
I see.
Pay just RAM runtime rather than Turing machine. I think it would still.
Okay, I see. T squared. Okay, I get it. Yeah, makes sense.
More questions? Yeah, sorry.
Just a high-level question about the final applications you mentioned.
Yes.
Are they all, like if we assume LWA and FHE, are they all really incomparable to each other? Have people even tried to show implications between them? Because it seems like, we have a growing number of primitives and maybe not so much effort to try to unify them.
No, I mean, I don't think, I think it's difficult to actually relate these primitives to FHE. I think roughly the difference is that
each other. Like the question is, you have like 5 different applications. There are 5 times 4, 20 applications. Whether all of them are hard if you further assume the WA and FHE, or just people haven't thought about it.
No. So okay, let me go to my implications. I don't think there is a general. Let me skip quickly. I think these two are actually different. I mean, you need. I don't know. I don't have a good answer, but here you actually need trapdoors. I mean, you need to do non-trivial things. I don't think just throw in there LWE.
I'm not saying they're all equivalent. I'm asking whether the 20 arrows are empty. Assume LWE and FHE.
No. And I think they should be all empty to the best of my knowledge. But I don't think there is any generic conversion across all.
Is there like a specific reason why Merkle tree to like compress all their hashes? Like for example, like from this like a recursive presentation, seems to me that reducing the height is the most optimal way.
Yeah.
So like.
Well, you also don't want your height to be, I mean, you want the height of your tree to not grow with the memory.
So like maybe there could be like a different data structure to bound the height more like flat.
Yeah, I guess you could maybe do it constant by increasing the arity a little bit. Maybe I'm not sure. I'd have to check. But I think the reason why we went for Merkle tree is just we're simple-minded people, so we just
Ah.
like our Merkle tree. So it's what we,
maybe there's a special reason.
no, it's just the easiest thing that worked. Yeah. But I should say I'm simple-minded. Maybe I shouldn't talk for my co-authors. Yeah.
All right, let's thank Giulio. Lunch, and we'll be back at 1:30.
1:30?
Sorry, 2.